You're tuned into the deep dive, and get ready because today we're really digging into the world of autonomous mobile robots.
It's a fascinating area.
It really is. We get this great source from you all, Learning Robotics, using Python 2nd edition. And our mission basically is to get a real feel for what it actually takes to build one. From that first idea
Yeah.
all the way to seeing it, well, move in a simulation.
Exactly. We're aiming for those key insights, the things that click.
Yeah, the aha moments.
Mm-hmm. This book, it really walks you through the whole process, designing it, simulating it, even programming the basic behaviors. We're going to try and unpack that whole journey.
Okay, let's get into it. It seems like a mix of different skills. The book talks about ROS, right?
Yeah.
Robot Operating System. But it says it's not quite a traditional OS, more like a meta operating system, which sounds intriguing.
Yeah, that's a good way to put it. It's more of a flexible framework for robot software rather than a complete OS like Windows or Linux itself. It provides the plumbing, you could say.
Okay, the plumbing. I like that. And then there's the actual physical design part, using CAD tools, LibreCAD, Blender, tools people can actually get their hands on.
Right, open source tools, which is great. And then you bring that design into this virtual world using ROS and another tool called Gazebo.
Ah, Gazebo. The simulator.
Exactly.
Yeah.
So you can test everything out, like, say, have your virtual robot deliver things in a simulated hotel before you build anything physical. It's pretty powerful.
And Python is in the mix too, not just for controlling the robot, but even, you mentioned, inside Blender for the 3D modeling.
Yeah, that's a really neat aspect. You can script parts of the modeling process. It shows how software weaves through almost every step. It's this blend, software, mechanics, even a fair bit of math.
Okay, so let's start with that plumbing then, ROS. If someone's building a robot, what's the main thing ROS does for them? Why use it?
Well, think of ROS like maybe the robot's nervous system. It lets all the different software parts, which we call nodes in ROS, talk to each other smoothly.
Nodes. Okay, like individual processes or programs?
Exactly. And they communicate by publishing messages onto specific channels called topics. So one node might publish sensor readings onto a sensor data topic.
Right.
And another node, maybe the navigation system, can subscribe to that sensor data topic to get the information it needs.
So specific channels for specific data. Makes sense.
Mm-hmm. And the messages themselves, they have defined structures. Could be simple things like a number or complex things like a full camera image or laser scan data.
Okay. And how does this all stay organized? Who manages these nodes and topics?
That's the job of the ROS master. It's like the central directory service. When a node starts up, it registers itself with the master, saying, "Hi, I'm here, and I publish on this topic," or "I subscribe to that topic."
Got it. So the master knows who's who and helps nodes find each other.
Precisely. Without it, nodes wouldn't know how to connect. There's also the parameter server, which is basically a shared dictionary where you can store configuration settings that multiple nodes might need access to.
Like settings for motor speed limits or sensor calibrations.
Things like that, yeah. And for more direct request response communication, ROS has services. And you can even record all the message traffic using something called bags, which is incredibly useful for debugging or replaying scenarios later.
Wow, okay. That sounds like a really comprehensive system for managing complexity.
Yeah.
What are the big advantages the book points out for using ROS?
Oh, there are quite a few. Number one is probably that seamless message passing we just talked about. It decouples the different software components.
Right.
Then there's hardware abstraction. This is huge. It means your higher level code, like your navigation logic, doesn't necessarily need to know the exact brand or model of camera or motor you're using. ROS can provide a standard interface.
So you could swap hardware components more easily.
Potentially, yes. Saves a lot of rewriting. Then there's package management. ROS has a system for organizing code into reusable units called packages. Think of it like libraries or modules, but specifically for robotics.
Like an app store for robot functions.
Yeah. Kind of, yeah. And it integrates really well with major third-party libraries. The book mentions OpenCV for computer vision, PCL for point cloud processing. You don't have to build those capabilities from scratch.
That must be a massive time saver.
Absolutely. ROS also helps with low-level device control, talking to the actual hardware. It supports distributed computing, so you can run different nodes on different computers if needed. Code reuse is a massive part of the philosophy.
Building on what others have done.
Exactly. And it's language independent. You can write nodes in Python, C++, A, sometimes other languages too, and they can all talk to each other. Testing is easier with ROS tools. It's designed to be scalable from small projects to complex systems, and maybe most importantly for many, it's free and open source.
That is a compelling list. Free and open source under the BSD license, the book says. And it mentions the ROS file system packages, meta packages. What's the structure there?
Yeah, it's just how things are organized. A package is the basic unit. It contains your code, launch files, configuration files, maybe the URDF we'll talk about later. A meta package just groups related packages together, and repositories are typically where these packages are stored, often on places like GitHub.
So it's all geared towards structured development and sharing. And if people get stuck, where do they go? The book mentions community resources.
Definitely. The ROS Wiki is the absolute go-to for documentation. There are official mailing lists and forums like ROS Answers, think Stack Overflow, but just for ROS, and the newer ROS Discourse platform. Huge amount of community support out there.
Okay, now getting practical. The book guides you through installing ROS on Ubuntu Linux. Is that the main platform?
It's certainly the best supported platform, yeah, Ubuntu. The book gives the specific commands to get it set up, adding repositories, installing the ROS distribution. It mentions ROS Kinetic, which was current then, but the process is similar for newer versions like Noetic or ROS2 distributions.
And it introduces Catkin. What's that?
Catkin is the build system ROS uses. It manages how all your different packages are compiled and linked together so they can work as a cohesive system. You run Catkin make, usually, in your workspace.
Got it. And to make this tangible, the book has a Hello World example, right? The classic publisher and subscriber.
Absolutely. It's the fundamental ROS communication pattern. It shows you how to create a simple package, then write two small Python scripts. One node, the publisher, sends out a basic hello world string message,
Okay.
and the other node, the subscriber, listens for those messages and just prints them out when they arrive. It demonstrates that core message passing idea.
Could you give us a tiny flavor of what that Python code involves? Just the key bits.
Sure. For the publisher, you'd import the ROSB library, that's the Python client library for ROS. And you'd import the message type you want to send, probably string from the st and estrees package.
All right.
Then you initialize the node using rosb.init node, giving it a name. You create a publisher object telling it the topic name to publish on, say, hello pub, the message type, string, and maybe a queue size. And then typically in a loop, you'd construct your message like my message, string data hello world, log it maybe, and use the publisher object's publish method to send it out. You usually add a rosb.sleep in the loop to control how often it publishes.
Okay. Sounds manageable. And the subscriber.
Similar start. Import rosb and the string message type. The key difference is you define a callback function. This function is what will actually do something when a message arrives. In this simple case, the callback might just take the incoming message object and print its data field.
So the callback gets triggered automatically.
Exactly. In the main part of the subscriber script, after rosb.init node, you create a subscriber object. You tell it the topic to listen to, hello pub, the message type, string, and critically, the name of your callback function.
Right.
Then the final line is usually rosb.spin. This basically just keeps the node running, listening for messages, and executing the callback whenever one arrives on that subscribed topic.
And the book mentions making the scripts executable and using Catkin make.
Yes, standard Linux stuff, you use chmod plus x on your Python files. Then you run catkinmake in your workspace root to build everything. And crucially, you need to source the setup file generated by catkin, usually source double setup.bash, so your system knows where to find your new ROS package and nodes.
All right, that gives a really solid picture of the ROS basics. The book then shifts gears to how the robot actually moves, focusing on differential drive. What's the idea there?
Differential drive is probably the most common setup for simple mobile robots, partly because it's cost effective. It just means you have two wheels, typically on the same axis, that can be driven independently, one left, one right.
And by controlling their speed separately, you can steer.
Exactly. If both wheels go forward at the same speed, the robot goes straight. If the right wheel goes faster than the left, the robot turns left. If they go opposite directions, it can spin in place.
A bit like a tank, maybe.
That's a perfect analogy, yeah. Each track controlled independently. The book then gets into robot kinematics.
Kinematics. That's about the motion itself, not the forces causing it.
Precisely. Kinematics is the geometry of motion. How does the robot's position and orientation change based on how its joints or wheels move? This is different from robot dynamics, which does consider forces, mass, inertia, friction. the physics behind why it moves that way.
Okay. And within kinematics, there's forward and inverse.
Correct. For kinematics is, if I know how fast my wheels are spinning, say V left and V right, where will the robot be and how will it be oriented after some time?
Predicting the future pose.
Yeah. The book gives the equations for this. They relate the individual wheel speeds and the distance between the wheels, usually called L, to the robot's overall linear velocity, how fast it's moving forward, and its angular velocity, how fast it's turning.
Right.
It introduces a concept called the instantaneous center of curvature, the ICC. Think of it as the point the robot is currently rotating around. If it's going straight, the ICC is infinitely far away. If it's spinning in place, the ICC is right between the wheels.
So the pivot point of its current turn.
Exactly. Knowing the ICC helps calculate the velocities. The book also shows how you can use data from wheel encoder sensors that count wheel rotations, NL and NR in the formulas, over a small time step to estimate the wheel speeds, and from there, update the robot's estimated pose, its XY position and theta orientation, from its previous pose.
So the robot can kind of track its own movement just by counting wheel turns? That's odometry, right?
That's odometry, yes. It's fundamental, but can accumulate errors over time. Then there's inverse kinematics, which is the opposite problem.
Okay, so if I want the robot to end up at a certain new pose, what speeds do I need to command the wheels to?
That's the question inverse kinematics answers, but the book points out an important constraint for differential drive robots. They are non-holonomic.
Non-holonomic, what does that mean practically?
It basically means it can't move sideways directly. Like a car, it can move forward, backward, and turn, but it can't just slide left or right. To change its lateral position significantly, it has to perform a sequence of movements, like turning and then driving forward. Not all changes in pose are instantly achievable.
Right, you can't just teleport sideways, you need a maneuver.
Exactly, but the book notes you can still achieve very precise positioning by carefully sequencing the wheel velocities over time.
Okay, understood. So we have the theory of motion. The book then makes it concrete with an example robot, ChefBot. What's its story?
ChefBot is the case study used throughout the book. It's imagined as a service robot for, say, a hotel or restaurant designed to deliver food and drinks to temples.
A practical application.
Yeah, and the book starts by listing out its key design requirements. Things like it needs to carry food safely, handle a certain payload, 2 kilograms, operate within a specific speed range, have enough ground clearance, run for a certain duration, avoid obstacles, fit within a height range, and crucially be low cost.
Those sound like realistic engineering constraints.
They are. And these requirements directly drive the choices for the hardware components. Selecting motors with the right torque and speed, RPM, choosing suitable wheels, designing the chassis or body structure, it all flows from those initial requirements.
And to actually design this structure, the book points to CAD tools.
Yes, specifically LibreCAD for 2D drawings and Blender for the 3D modeling. A big plus is that both are free and open source and run on multiple operating systems, making them really accessible. It also mentions MeshLab, which is handy just for viewing 3D models.
That open source aspect really helps people get started. How does the design process flow in the book's example?
It shows creating 2D technical drawings in LibreCAD first. Things like the base plate, the support structures, wheel mounts, caster wheel placement, the different levels or plates of the robot. It gives some example dimensions.
Okay, the 2D blueprints.
Then it moves to Blender for the 3D model. And here's where it gets really interesting. It shows how to use Python scripting inside Blender.
Right, you mentioned that earlier. Using Python to build the 3D model.
Exactly. Blender has a built-in Python module called ByB. The book provides a script that uses ByB functions to programmatically create the 3D shaped cylinders for poles, cubes for bases, importing wheel models, maybe assembling the entire ChefBot model piece by piece through code.
Wow, so you're literally coding the robot's physical form.
In a way, yes. And once the script generates the model in Blender, it then uses Python commands again to export the whole thing or individual parts into the STL file format. STL is very common for 3D printing and simulation.
Okay, so now we have a 3D model of ChefBot as an STL file, maybe several STL files for different parts. How does ROS understand this?
That's where the URDF comes in. Universal Robot Description Format. It's an XML file that describes the robot structure to ROS.
XML, okay. What does it describe specifically?
It defines the robot's links. Those are the rigid body parts, like the base, a wheel, sensor casing. And it defines the joints that connect these links, specifying how they can move relative to each other, like a wheel joint rotates, an arm joint might pivot.
So the skeleton and how it moves.
Pretty much. The book also introduces Zacro, which stands for XML macros. It's a way to make URDF files cleaner and more maintainable. You can define constants, use simple math, include other files. It makes complex robots much easier to describe.
So Zacro helps manage the complexity of the URDF, and this URDF tells ROS about the robot's shape and connections.
Yes, its geometry, its visual appearance, often linking to those STL files for the shapes, its collision geometry, how it interacts physically, and even its inertial properties, mass, center of mass, moments of inertia, all crucial for simulation and control.
Okay, and how is this URDF file organized within ROS?
You typically create a dedicated ROS package just for the robot's description. The book uses ChefBot description as the example. Inside this package, you'd likely have a meshes folder containing your STL files, and a ERD or Zacro folder containing the actual URDF's acro files defining the robot structure.
And how does ROS actually use this information during runtime?
There's a standard ROS node called Robot State Publisher. Its job is to read the URDF file and listen for information about the current state of any non-fixed joints, like wheel angles from odometry. It then calculates the 3D position and orientation, the pose of every link in the robot based on this information.
Okay.
And it broadcasts these poses using ROS's transformation system called TF. TF maintains a tree of coordinate frames, allowing any other ROS node to easily ask, where is the left wheel relative to the base? Or where is the sensor relative to the map? It's fundamental. The book shows simple Zacro examples defining links like base link and a fixed joint connecting it to base footprint.
Right. TF keeps track of where everything is in 3D space.
Okay.
So theory, design, description. The next big step has to be simulation, seeing ChefBot move in that virtual hotel.
Exactly. And that's where Gazebo comes in, which the book introduces as a powerful 3D simulator that works very well with ROS.
Gazebo, what's it like to use it?
It has a graphical interface. You see the 3D scene with your robot in its environment. There are panels to insert models, manage simulation properties, inspect objects. The book points out key things like understanding the difference between simulation time, which is time passing inside the simulation, and real time, actual clock time. The ratio between them is the real-time factor, or RTF.
RTF. So you know if your simulation is running slower or faster than reality.
Precisely. An RTF of 1 means it's running in real time. Less than 1, it's slower. Greater than 1, it's faster.
So Gazebo is the virtual sandbox. The book suggests starting with a TurtleBot simulation first.
Yeah, that's good advice. The TurtleBot is a standard platform. Lots of examples exist. Simulating that first helps you get familiar with Gazebo and its ROS integration before tackling your own custom robot like ChefBot.
Makes sense. So when we do bring ChefBot into Gazebo using its URDF, what special considerations are there for simulation?
The book highlights 2 crucial tags within the URDF, collision and inertial.
Collision and inertial. What do they do?
The collision tag defines the geometry used by the physics engine for detecting collisions. It might be simpler than the visual mesh sometimes for efficiency. Without it, your robot might just fall through the floor or drive through walls.
Okay, essential for physical interaction and inertial.
The inertial tag specifies the mass properties of the link, its total mass, center of mass location, and its moments of inertia. These tell the physics engine how the link will react to forces and torques. Without accurate inertial properties, the simulation won't behave realistically.
Got it. Visuals, collision shape, and mass properties all needed.
Yes. And the book also mentions Gazebo-specific tags you can add within the URDF inside a Gazebo element. These let you set simulation-specific parameters like friction coefficients for wheels, or importantly, specify Gazebo plugins.
Plugins, what do they add?
Plugins are like extensions that add functionality to Gazebo models. For ChefBot, the book mentions the crucial differential drive plugin. This plugin reads the velocity commands sent from your ROS control node via a topic, and applies the appropriate forces or velocities to the wheel joints in the simulation, making the robot move.
Ah, so the plugin connects the ROS commands to the simulated physics.
Exactly. There are also plugins to simulate sensors. You can add a plugin for a laser scanner, a depth camera like the Kinect mentioned for ChefBot, cliff sensors, contact sensors, even an IMU or gyroscope. These plugins generate simulated sensor data and publish it on ROS topics, just like real hardware would.
So your ROS nodes can consume this simulated sensor data as if it were real.
Precisely. That's the beauty of it. You can test your perception algorithms, your control loops, everything, using purely simulated data.
And can you see this data?
Yes. The book explains how to use ARVIS, which is ROS's primary 3D visualization tool. You can configure RViz to display the simulated laser scans as points, the depth camera data as a point cloud, the robot model itself using the TF data, the planned path, everything. It gives you incredible insight into what the robot is seeing and doing in the simulation.
That sounds incredibly useful for development and debugging. Now the book moves towards more autonomy. SLAM. Simultaneous localization and mapping sounds complex.
It is a classic robotics problem, but fundamental for true autonomy. SLAM is basically the task of putting a robot in an unknown environment and having it build a map of that environment while simultaneously figuring out where it is within that map it's building.
Doing both at the same time. Wow. How?
The book introduces a popular ROS package called G-mapping. It implements a well-known SLAM algorithm.
Okay, G-mapping. What does it need to work?
Typically, G-mapping needs two main inputs. Laser scan data, usually from a 2D LiDAR published as a laser scan message, and odometry data, the robot's estimated movement from wheel encoders, usually a Navin's aldometry message.
Laser scans and movement estimates.
Right. Using that, G-mapping builds a 2D map, represented as an occupancy grid, basically a grid where each cell has a probability of being occupied or free space. It publishes this map as a NavOmsG's occupancy grid message. The book shows how to run G-mapping with the simulated chef bot in the hotel world and view the map being built in real time in our viz.
So you can watch the robot explore and literally draw the map as it goes. Amazing.
It really is cool to see. Now, once you have a map, maybe you save the one built by G-mapping, the next problem is just localization, figuring out where the robot is within that known map.
Right, because odometry drifts over time.
Exactly. For that, the book introduces AMCL Adaptive Monte Carlo Localization. It's implemented in the AMCL ROS package.
EMCL Monte Carlo. Does that involve randomness?
It does, in a clever way. AMCL uses a particle filter. It maintains a large set of particles, maybe thousands of them, scattered across the map. Each particle represents a hypothesis of where the robot might be. It's pose.xy theta.
Okay, a cloud of possibilities.
Exactly. Then, as the robot moves, using odometry data, and gets sensor readings, like laser scans, AMCL updates these particles. Particles whose hypothetical poses match the sensor readings well get higher weight or probability. Particles that don't match the sensor data get lower weight or are even removed and replaced.
So the particles converge towards the most likely actual location.
Precisely. Over time, if things are working well, the particle cloud will shrink and cluster tightly around the robot's true pose on the map. The book explains how to run AMSOL in the simulation and even use a tool in our viz called 2D Pose Estimate to give AMCL an initial guess of where the robot is starting, which helps it converge faster.
Okay, so a SLAM to build the map and ANCL to know where it is in the map. That sets the stage for actual navigation, right? Getting from A to B.
That's the final piece. The book briefly touches on enabling ChefBot to navigate autonomously in the simulated hotel, maybe going to specific tables. While it doesn't dive super deep into the ROS navigation stack itself, which handles path planning, obstacle avoidance, and motion control, it shows how all the previous steps, modeling, simulation, mapping, localization, are the essential prerequisites for achieving that kind of goal-oriented autonomous behavior.
It really is a logical progression, isn't it? From the absolute basics of ROS communication, understanding how the robot moves, designing it virtually, describing it for ROS, and then simulating its interaction with the world, including mapping and localization. It's quite a journey.
It covers a huge amount of ground, yeah.
So if we were to boil it down, what are the absolute key takeaways from exploring this book?
I think the main thing is understanding that building even a relatively simple mobile robot involves integrating multiple disciplines. You need the software framework like ROS, the understanding of kinematics, the mechanical design skills using CAD, the ability to describe that robot formally with URDF, and then the power of simulation with tools like Gazebo to test perception like SLAM and localization like AMCL before you even touch hardware.
It provides a really solid roadmap, a foundation.
Absolutely. It shows how Python and ROS can be powerful tools to tie all these pieces together, making robotics development more accessible.
It really does. And thinking about that simulation aspect,
Yeah.
it makes you wonder, doesn't it? How much does the ability to design, test, and refine robots entirely in simulation accelerate progress? Not just for service robots, but think about manufacturing, logistics, even space exploration.
It's a massive accelerant. It lowers costs, reduces risks, allows for rapid iteration. It fundamentally changes how robotic systems can be developed.
Which leads to a thought for everyone listening. Think about your own work, your own interests. Where could this ability to simulate complex autonomous systems before building them Where could that make a difference? What problems could it solve? Or what new possibilities might it open up?
That's a great question to ponder. How could these tools be applied in unexpected ways?
Definitely something to think about. If folks want to dive deeper after this, where should they go?
Well, the book itself likely has a companion code repository, probably on GitHub, that's always invaluable for seeing working examples. The ROS Wiki is the ultimate reference for any ROS concept, and honestly, just downloading LibreCAD and Blender and playing around with them is a great way to get a feel for the design side.
Get your hands dirty, virtually speaking.
Exactly. Start simple, build a virtual box robot first.
Good advice. This has been incredibly insightful. We've covered so much, from ROS nuts and bolts to virtual robots navigating hotels.
It's been fun digging into it. And there's always more to explore in robotics, advanced perception, manipulation, control theory, maybe topics for another time.
Sounds like a plan. Thanks again for sharing your expertise today. And thanks to all of you for joining us on the deep dive. Until next time, keep exploring.